Hi, welcome to part one of the basics. Here we're going to discuss the fundamental variable. Here we'll talk about two variables that impact motion mechanics, the study of motion. We'll go straight into it. We'll start with the first variable. Anything, when we study motion, any object that moves, we need it to move across space. There has to be a distance or some kind of something that represents the spatial aspect of how much it moves. So our first variable here is going to be distance, right? I'll put that here. And I'm going to use uppercase S to denote distance. And we'll use this as we go on, right? So S. I'm also going to introduce another term called displacement. And you will find some textbooks, some problems that will use these words interchangeably, but let's go over what they actually mean, right? And we'll illustrate that by saying, here's an object, and we have it moving to, let's say, here. And let's say that's about 30 centimeters or so, right? So we could say S is equal to 30 centimeters. The object has traveled a distance of 30 centimeters. Distance, right? The object is displaced by 30 centimeters. That's displacement. But now let's take another case where the same object is here. We have it move and come back here. Now what happens? What is the distance the object has traveled and what is the displacement? You could argue here that this length would represent how much the object has been displaced by, right? It's fine, its initial position, its final position, and let's say this is 20 centimeters of displacement. But what is the distance traveled? It's gone from here to there, and then it's traveled there, right? It went up this way, and then it came back this way. Which means its distance is actually, say, if this was 20 and that's 30, so this is 10 centimeters, that was 30. So here, 40 centimeters would be distance. Important to understand this. Some books position these terms interchangeably. Sometimes they give you displacement, which is really just distance. Sometimes they'll give you displacement, but there might be something else in the question that might point calculating distance separately. So important to keep that in mind. Right, I'll take that off and we'll get to the next. Actually, we'll leave this on now and talk about the next variable so it gives you some perspective. And the next one we'll talk about here, we'll write that here, is time. And I'm going to denote time with a lowercase t, right? Let's say we took 2 seconds to travel, in which case the time would be 2 seconds. We went up here in 2 seconds and we took another second to come back. Total time would be 3 seconds. 40 centimeters traveled in 3 seconds. 30 centimeters traveled in 2 seconds. And remember, time is always a period between two observations, two instances. It's not absolute, so I wouldn't say it's 10:35 a.m. in the morning here. That's not the measure of time. Time is the number of, or the units of time that is measured between two observations, right? Two positions. So keep that in mind. One more important factor to remember, distance is measured mostly in meters. We'll use another color for that. Mostly in meters, and time is measured in seconds, usually, right? You might find problems that position kilometers, hours, minutes, centimeters, as I have here, but these are some important things to remember. Okay. Using these two, we'll introduce a few more variables that come in. Right? I'll take this off and get to the things that we can build using distance and time. First one we'll introduce here is velocity, and we'll put that here. We will use lowercase cursive v to represent velocity, and velocity is simply how much distance or did you travel, or what distance has passed in the time that has passed. So it's the change in, or represented sometimes the change in distance if you're using absolute coordinates of distance, to the change in time. You could consider that as a first derivative of distance to time. But for simple purposes, simple problems, it would simply be distance divided by time. And in our case, that would be, for case S, divided by t. In which case, you would denote velocity in, let's use green to be consistent, in meters per second, sometimes also written as meters second this way, which is probably how we will be denoting as we go through problems, right? That's the next piece that we've introduced. So I'll take that out, simplify this here. So velocity in meters per second. Okay, here I'll introduce the concept of initial velocity and final velocity. But before we get there, here's another thing I want to show you. So if I wrote v is equal to s over t, I would also be able to write s is equal to v times t. That's really nice, because now we can introduce a little bit of fun with coordinate geometry and say if I had two axes here, one measuring velocity and the other being time, and if I had a velocity of v and a measure of time t, product of the two, which is the area here, would simply be s. And we'll build on this further when we go into the intermediate section of the videos and we discuss this. We'll come back and revisit this and why using this method is kind of nice to visualize what's going on. But I thought I'd give you an introduction to that. Okay, take that out for the time being. And also talk about some more interesting things with velocity. Sometimes you'll find initial velocity. I'm just going to use VEL for short. And that gets represented sometimes with U, will also be meters per second, and you'll find final velocity. And that gets denoted almost always with cursive V, also meters per second. So if you had this and you're in a situation where, let's say, you were traveling at U meters per second, and then for some reason you've now moved to v meters per second, the change of velocity, if you will consider a derivative of velocity with time, so let's say in 10 seconds you increase your velocity, that means your velocity has gone up. That introduces us to the next most important variable that we'll develop, and that is called acceleration, almost always denoted as A. And you might say in simple terms, A can be thought of being equal to final velocity v minus initial velocity u, which is the change in velocity over time lapsed. And if velocity is meters per second, time is in seconds, that would give acceleration the unit of meters per second square. Something important to remember, right? So in practical terms, if, let's say you got let's say an engineer told you that he has an incredible engine that can generate, let's say, an acceleration of 1,000 meters per second squared, you could say, well, if I put that in a car, and the car is at rest, after say 10 seconds, what would the car's speed be? You could manipulate this equation and kind of build on it and come up with a few different calculations. You could say final velocity v is equal to, and you can look at the math here, it's nothing but u plus a times t. So if you were at rest, then your final velocity would simply be acceleration times time. Right? So once you have u as 0, velocity is just acceleration times time. You can go back and plot that on the graph, and we can see some interesting things develop out of it. So, two basic variables, distance and time. We've built velocity, we've built acceleration, and then when we get to part 2, we'll add a few more basic variables and build out a few more interesting pieces here, right? Till the next video.